Today we are going to discuss one of the most important problems in physics, particularly high energy physics, that is known as spin crisis of the proton. It is still considered to be one of the most important unsolved problem in physics. Before I start discussing on this crisis, I want to remind you about the history of physics little bit. Actually, before 1908, we did not have the modern idea of atom. What we know now, that there is a nucleus and there are some electrons revolving around the nucleus. This modern idea of atom, this modern picture of atoms, we did not know before 1908. But during 1908 and 1913, there was a famous experiment. This was done by Rutherford, Lord Rutherford, and from that experiment is known as Rutherford alpha scattering experiment. And from that experiment, what is done, a alpha particle was allowed to incident on the proton, actually gold proton, gold nucleus, gold atom, atoms of the gold. An alpha particle was allowed to incident or strike a gold plate where there are gold atoms, and with this scattering experiment, after analysis, people came to know what is the structure of atom. Before that, atom was considered to be the elementary particle. So, but after that we came to know that actually atom is not an elementary particle, it has some internal structure, and that structure is that it has a nucleus. This nucleus is positive, where there are some protons and neutrons, and some negatively charged electrons revolve around the nucleus. So, this is the modern picture of atom. And about 60 years later, similar type of experiment reveals something different. That experiment, the alpha scattering experiment, when the alpha particle was allowed to incident upon some gold atom, then with this experiment we came to know about the internal structure of the atom. In a similar way, 60 years later, almost 60 years later, there was some people did some proton-proton collision experiment, and with this help of this proton-proton collision experiment, people came to know that proton, the constituent particle of the nucleus, this proton is also not an elementary particle, it has also a composite structure, it has also an internal structure, and that structure is that proton is made of some quarks. Proton is made of two up quarks and one down quarks. It is almost similar experiment. Now we do not consider this proton to be some elementary particle. This is the modern picture of proton we came to know after 70s. But this proton, structure of the proton, that it is made of some quarks, two up quarks and one down quarks, then how these quarks make, or how these quarks make the proton? Proton is a fermion. All of us we know in high energy particle physics. This proton has the internal spin angular momentum, it is h cross by 2. This proton, this spin angular quantum number, it is h cross by 2, we know it. And those quarks, up quarks, two up quarks and one down quarks, there are three quarks inside proton, and two of the quarks have spin parallel to the spin of the proton, and one of the quarks has spin antiparallel or opposite to the spin of the proton. So finally, all total, or if you add up the spin angular quantum number of all those quarks, it ultimately makes the spin angular momentum of the proton to be h cross by 2. It was initially thought, initially it was believed, initially it was speculated, but in 1987 there was a famous experiment which disturbed all the beliefs about the proton. How did it disturb? That experiment, that famous experiment, is known as EMC experiment, European Muon collaboration experiment. European Muon collaboration experiment. It was done in 1987 and 88. But this European Muon collaboration experiment is shattered all the hopes of the high energy physicists about the spin angular quantum number, spin angular momentum of the proton. We believe that there are two quarks which have spin angular momentum parallel to the momentum of the spin of the proton, and one quark which has spin opposite to the spin of the proton. We believe like that, but that is not. European Muon collaboration experiment done in 1988, it showed that these quarks contribute only maximum 24% of the proton spin. It can explain maximum 24% of the proton spin. So where does the remaining part of the proton spin go? Where did it go? That was a puzzle. That is called spin puzzle. That is called the spin crisis. Later on, different experiments, series of experiments were done in course of time, and in those experiments we gradually started to learn that some parts of the remaining part of the spin angular momentum of the proton, it is carried by the orbital angular momentum of those quarks. Some part of the spin of the proton or spin angular momentum of the proton is carried by the gluons. These gluons are the particles because of which those quarks they stick together. Because of these gluons carry the strong force. Because of this strong force, one quark and other quark, they stick together, and those gluons also carry some part of the proton spin, and those gluons can produce some quark antiquark pairs also. Quark antiquark pairs, those large number of quark antiquark pairs they can produce, and those large number of quark antiquark pairs, they also carry some part of the proton spin. So that is the modern idea, but it is still, there are some doubts. It is not confirmed yet. There are lots of things to be confirmed regarding the internal structure of the proton. That means the spin crisis of the proton is yet to be fully solved. We do not know exactly the exact picture of the exact internal structure of the proton, and that is known as the spin crisis. And that is why the modern picture of our proton is like that, this diagram. So this is the modern picture of the internal structure of proton. It is very complicated. It was not as we thought before 1987. You see, this is one quark, this is another quark, this is another quark. These are three quarks. For some reasons, we will not discuss here. For some reasons, these main quarks, they are called the valence quarks. And originally, we thought that this quark has a spin. Suppose it is one U quark, it is another U quark, it is D quark. Two U quarks, and we remember that we should remember that two U quarks and one D quarks, they make a proton mainly. So this is U quark, this is another U quark, and this is D quark. And suppose this proton has spin angular momentum up, h cross by 2 up, and this U quark has spin angular momentum up, this U quark has angular momentum suppose up, and this U quark has angular momentum down. So up, down cancel, and this up, it will remain, so it will make the spin of the proton. So it was thought initially before 1987, these for some reason this quark, this quark, this quark, they are called valence quarks, and these valence quarks carry the entire amount of spin angular momentum of the proton. It was thought before 1987. But after 1987 and the following development in high energy particle physics, it showed that it is not like that. These valence quarks, they are bound with each other, they stick with each other. Different numbers of gluons. Suppose this is this yellow ball, this yellow ball, this yellow ball. These are suppose gluons. These are gluons. These are gluons. Because of these gluons, because of these gluons, they stick together. Because of these gluons, they remain attracted to each other. These gluons are the carriers of strong nuclear force, and these gluons, they can produce or they can generate quark antiquark pairs. So there are large number of other quarks also come into the field. There are large number of other quarks besides these valence quarks. There are large number of other quarks produced by these gluons. Gluons, it does two important things. One thing is that it, because of these gluons, those quarks, they stick together, and the another work it does is that these gluons, they can produce quark antiquark pairs, large number of quark antiquark pairs, and because of this large number, we call all these quarks C quarks. C. So, and the modern picture of the internal structure of the proton is that around 20% of the proton spin is carried by these valence quarks, and remaining parts of the proton spin is carried by these gluons and all those C quarks. But how do they exactly carry? What is the exact amount of the contribution of different components towards the spin of the proton? We still do not know. And that is one of the unsolved problems of high energy physics, particle physics. So with this, I like to conclude. Thank you.